Good. You didn't remember to bring that square reader, did you?
Testing. Test. 1, 2. Testing. Test.
You are doing
1, 2, 3. Test. Test.
I respect that. You're gonna head down to Kiwi though?
Yeah.
So I'll see you there.
Yeah, I'll bring my lectures.
Testing.
Cool.
Okay, we're good to go. We're live on the HN2, so thanks, Graham.
Thanks very much, Pam. Good evening, everyone. My name's Graham Kotchu. Thanks for having me here. I've been a ham for many years. I think Max talked about legality, and when I was about 18, we introduced CV radio to Australia in the days when there was just one channel, 27.240 and 1 watt transceivers, and we brought in the first 23 channel sets which ran 5 watts. And it wasn't long before we attracted the attention of the radio branch, and I was given an alternative. So I got my license. And radio. So that's the introduction to my love of radio was really spawned from pirating in the old days, and buying crystals and making single transistor transmitters and stuff like that. And of course, what you realise is that antennas are a critical part of ham radio. I think Max touched on that before. And if we look at the 3 essential components of software-defined radio, we've got our HAC RF1s and our RTL SDRs. We've got the feed line that's going to connect them to an antenna and the antenna. And I suppose what a lot of people just only experience playing with the little whip antenna that comes with their RTL SDR and may end up giving up in disgust or dismay that they can't pick up very much, and that's where a big antenna really makes a lot of difference. Optimising your antenna makes a big difference to your enjoyment of SDR. Because what antennas do is that they convert electrical energy into electromagnetic energy, and vice versa. Obviously, they're reciprocal, transmitting, receiving, and they're the only link that you've got between your software-defined radio and the rest of the universe. And I say universe, not likely, in the sense that even with a cheap RTL SDR, you can actually hear the hydrogen line coming from other stars if you're in the right environment with a low noise amplifier and a good antenna. So from my perspective, I think antennas are critical because they can make or break your experience with software-defined radio. Just about every antenna is has its origins or based on the half-wave dipole. And the half-wave dipole refers to the length of the radio wave in free space, and that's about, for 300 megahertz, the wavelength is about 1 meter, and half of that, half a meter for about 300 megahertz. What a half-wave dipole does, which I'm showing here, which is a half-wave broken in the middle and fed with coax, is that if we look at the screen where we can see the radio waves coming along, impinging on one half of the antenna, the red signal is the voltage and the blue signal is the current. Coming up and looking at this other diagram, the way one of the features of a half-wave dipole is that the impedance at the end is infinite and the impedance in the middle is around 50 ohms. So that's why you'll see that there's never a large current at the end of an antenna, but there's very high voltage because it's effectively a very high impedance. And if it's cut to the correct length for a certain frequency, then we say that that antenna resonates at that frequency and it's the optimum length for receiving that frequency. An antenna, if we look across the left, that's a vertical half-wave dipole. It radiates out electric field, but at the same time, of course, because there's current flowing up and down, and you think of the, forget the law, but yeah, this one, yeah, the magnetic field will actually, it'll be sending out a horizontal magnetic field as well in response to the alternating current going up and down. So that's a very, very brief description of the theoretical aspects of an antenna design. But in the real world, obviously, if you want to vary your frequency, you can't go out and start cutting ends off your antennas and adding bits of extra length. So we are nearly always dealing with non-ideal lengths for our antennas. We're also dealing with the problem of limited bandwidth, especially with software-defined radio. You've got a hack RF, which will go from, say, a megahertz to 6 gigahertz, and you're plugging in a little whip antenna. Well, at 6 gigahertz, it should be about that long, and at 1 megahertz, it should be about 300 meters long, or give or take. So we're hardly ever going to be working with an antenna that is necessarily suited to the area of interest that we're looking at, considering we can swap decades of order of magnitudes of frequency at a whim with something like GQRX. You just change your left-hand column and you've jumped up a gigahertz. We also have physical limitations in implementation. If you look at something like the ideal antenna, you may not have space to fit that in. You may not have the ability to actually hold it in the air away from many obstacles without, well, you have physical limitations in actually how you can place antennas to work well. Next limitation is the feed line loss. If you have, depending on the size of the coax that you're using and the length that you're running it over, you suffer loss in your feed line. And the longer it is, the more it drops, the more loss you have. The higher the frequency, the more loss you have. And it's another thing to be aware of, that it can have a big impact on getting the signal, which might be okay at the antenna. By the time it hits your radio, it can be diminished. Another problem with antennas that we find is co-location interference. I think we saw a big picture of multiple antennas all in the same place before. Cell towers and tops of buildings, you'll see arrays of antennas. Nearly all of those are transmit and receive, and of course they're going to be pumping out 50 or 100 or 1,000 watts in certain directions, and you've got your antenna right next door, and you can suffer all sorts of cross-modulation and interference because of the strength of the signal that's coming in, not in your area of interest. And lastly, of course, the weather. If you hike up in the hills in winter or cross-country ski like I do, you see antennas dripping with ice, weighed down by snow, covered in snow. If you live down near the beach, you know, everything corrodes. You put something nice up, nice and shiny, and 3 years later, it's just covered in corrosion, and that affects connections and the like. So how do we go about solving these real-world problems of, first of all, length? What we can do is we can use matching networks to, it's important in all manner of radios that receive and transmit that you match the impedance of your radio with the impedance of the antenna. And the way that we do that is using inductive and capacitive coupling. And they're called matching networks, a subject for another talk. But what they can do is appear to make an antenna look like it is at the resonant length for you. Limited bandwidth. If we look at a single antenna, it'll be cut for a certain frequency, one frequency. But what we can do is have different designs of antennas like the log periodic antenna and fractal antennas, which I'll show examples of later, that actually cover a significant swath of bandwidth, sometimes up to an order of magnitude frequency range, like 1 gigahertz to 10 gigahertz, all just with one antenna. Once again, as with physical limitations, the ground plane is often, if you think about a half-wave dipole, it's got the 2 quarter-wave sections and you're feeding it in the middle. You can't drive around with a half-wave dipole sticking out the window of your car. But what you can do, you can put the top half of it, chop the antenna in half and use the top quarter-wave dipole, attach that to your roof and use the roof as a ground plane. And the ground plane looks like a mirror and it reflects that top quarter wave and it gives you an imaginary quarter wave and going down inside the passenger compartment of your car. So as far as the feed point of the antenna is concerned, all of a sudden it's got a virtual reflection of itself, and it's now appears to be more like a half-wave antenna. That's one way around the limitation of fitting something that is isolated in space into something that's attached to a moving object. Ways of overcoming feed line loss. You spend lots of money and buy really thick heliacs, which is a very expensive, very low loss form of coaxial cable. And the other way of doing that, overcoming feed line losses, to actually have a low noise amplifier right up at the antenna, which is only useful for a receive situation, obviously, but you amplify the signal before it goes down the feed line, and so any loss that you've got in the feed line becomes negligible. Ways of overcoming co-location interference include having antennas with the design of a high directional antennas that have a high back to front ratio, we say. So they looking out this way, they've got high gain. Looking back that way, they've got very low gain. So they effectively ignore what's behind them and they're only interested in what's out in front. And if you carefully locate your antennas in an antenna farm so that they don't point at each other, that's a good start. But in some cases, especially when you're talking about repeaters, we looked at what repeaters were just before, you've often got a very close, say, amateur repeaters, often 600 kilohertz split at 144 megahertz. That's a very close signal with, if you've got a transmitter at 100 watts and only 600 kilohertz away you've got your receiver, it's very easy to deafen the receiver, because as soon as the receiver gets the signal, it'll immediately plug that audio straight into a transmitter and shove it out at 100 watts right next door. So what we use there is a thing called a cavity filter, which is a cylinder that's very, it's tuned to the frequency of the transmitter in this case, and it's a very, very high Q filter, which means it's a very efficient filter. It's got a very narrow bandwidth, and it's probably up to 50 or 60 dB notch, so it can really knock out that transmit signal. It'll just completely wipe it out of the receive chain. And lastly, radomes are a typical way of overcoming weather situations, but you'll often see microwave dishes in a hemisphere, or even radar, all of the white domes that hide, you don't know what's inside. It's double purpose. You can't see where the antenna inside is pointing, you can't see what its characteristics are, and it gives a fair amount of privacy for the antenna owner. You don't know where it's pointed even. Similarly, most vertical antennas that you'll see, commercial ones, are in a radome, effectively a big piece of white plastic. Inside there'll be probably a collinear or matching elements, all sorts of electronics inside that, but they're shielded from the weather by a piece of PVC piping. just briefly, I think in a previous talk, one of the speakers showed the construction of a simple ADS-B antenna. Now, effectively, with the way an ADS-B antenna works, my mouse has gone to sleep. The top half of the antenna is a half wave length, which is the actual radiating or receiving element, and the bottom half is a loop, and it's a quarter wave stub. And on that, you shift your coaxial connections and moved up or down that stub to find the right position to balance out the reactance of the natural reactance or impedance of this antenna to provide a good match for a 50 ohm load or a 50 ohm piece of coax which goes off to the radio. That's just an example of a passive matching network. Now I just want to ask you a question. Is this fact or fiction that any scrap of metal can be a good antenna? Yeah. Can we listen to Triple M out of a paperclip? Well, the answer is yes, you can. Just as long as any piece of metal is really correctly matched to, talking about matching, it's matched to the transmitter in this case, it will work, and all of the power that the transmitter is putting out will be radiated out by that piece of metal. If it was Triple M, that paperclip would melt, obviously, but the disadvantage is, of course, it's going to be effectively a point source transmission or a monopole transmission. So the radiation direction will be isotropic. It will go equally in all directions, just like the sun. And that's not much fun. Not many people want their signal to go in every direction all at once. And so that brings me to antenna design, because really the main reason that we do anything with antenna design is to take control of the radiation pattern or the radiation direction. This is a rather big statement, but if you think about it, that's what antenna design is about. So this is a diagram effectively giving you that feeling of what an isotropic radiation looks like. It's going out in all directions from a point source, and it's a theoretical concept, but if we plot that radiation on a 2D chart, it just will be a smooth ring of power at around about, by definition, 0 dB, because that's what most antenna gains a reference to, is the isotropic transmission. What we want to do when we play around with designing an antenna is to maximize the power that's radiated in one direction only, and try and minimize any radiation in the rear direction and minimize side lobe radiation. There will always, in nearly every antenna design, will have some back radiation and some side radiation, but we can design an antenna to minimize that. Common types of directional antennas that you will have come across are the Yagi antenna. TV antennas are a bastardized version of that. You'll see them on tops of power control boxes in the city, even some in the old days on top of traffic light control boxes. There'd be a little Yagi sometimes pointed in a certain direction. The parabolic dish, all sorts of varieties this comes in. This is like a little mesh version of a parabolic dish. A radio telescope's the most serious version of that. Helical antennas, don't see these very often, and I'll talk about polarization in a little while, but these are circularly polarized and most often used for satellite work. And panel antennas, like a cell phone tower, inside that box there'll be like 8 or 16 little patch panel antennas all phased together and they're quite subtle. They can be sort of built into a wall and just look like a light fitting. Omnidirectional antennas, on the other hand, which are, if you're just playing with your SDR and you don't know where you want to listen to, but you just want to get some gain, you've got a couple of options. The disc cone, which is a large frequency, covers a large frequency range and provides some gain. And that will be omnidirectional. It'll mainly, it gets its gain from pushing out in the horizontal direction. Nothing much goes up, nothing much goes down. So think of a donut of radiation coming out of that. And the collinear antenna, which is normally, inside that there'll be a series of half-wave sections in alternate phase, all soldered to each other, and that effectively what it does is it narrows down the radiation beam to become narrower in the horizon. But once again, it's a donut, a toroidal sort of construct. What some of the other important considerations if you're actually sitting down to design an antenna, obviously you're choosing the size of the radiating elements for your frequency and the bandwidth that you're trying to manage to work over. And this is where a log periodic, this is an example of a log periodic antenna. You'll see that it's got a number of half waves in descending size, and that's where you get your some directional gain out this way, but at the same time you're covering a large frequency range. Just briefly touching on polarization, because that's something that is quite important with antennas too. If the radiating element's vertical, then it's said to have a vertically polarized signal. Similarly for horizontal, in the very early days, just about all radio was horizontally polarized because everyone was using big half-wave dipoles strung up between two trees or two poles. And of course, power lines are also horizontal. So there's a lot of interference from power lines because that's also horizontally polarized noise. So there's a move in the early days of radio to going over to vertical polarization, even on we're talking about high frequency band between 3 and 30 megahertz. There's a 20 dB difference between, if you try and receive a vertically polarized signal with a horizontally polarized antenna, you'll get a 20 dB reduction in power, bring it back up vertical. So there's a good margin of isolation between the two polarizations. Going back to the helical antenna we looked at before, it's physically built as a spiral, and that gives you a circularly polarized signal depending on which way the spiral goes. It can be right-hand polarized or left-hand polarized. Space transmissions often use circular polarization because it gives, once again, good noise immunity from terrestrially generated interference. So if you've got the correct polarization on your receiving antenna, you can get some margin of isolation from local noise. There are other polarization techniques, and there's a lot that I'm leaving out. The antenna theory is it's quite complicated, and there's lots of other features that I'm sorry I haven't got time to mention here. But two other things to think of is the physical size of the antenna that you're trying to put together, how many elements you're going to manage to fit on the boom before it drops and starts falling down, and wind loading, because that's a big issue. You've got an antenna on the roof, as I do, that goes up really high, and you get these 80, 90, 100 kilometre an hour winds. You're a bit worried that it's going to fall over on the neighbours. And lastly, of course, visual impact. You've got something like that in your front yard, your neighbours probably think you're building a death ray. And so there are many, many different types of antennas. There are at least 20 different types. But some of the ones that are more interesting, I think, are slot antennas. Now, they're usually used at microwave or very high frequencies, and that's a slot antenna works by having a hole in a piece of metal, and you actually excite the metal and the radiation comes out the hole. But horn antennas that you've seen, like used at microwave frequencies, they're a variant of a slot antenna. Low profile antennas, low profile visually and from physically. A good example of this is GPS antennas on the back of a car. Some people try and make them look like shark fins, I don't know, to differentiate themselves, but there's no real need to have them like that. Fractal antennas I mentioned before, I think these are really cool. Just as a coastline has a fractal shape or a fractional geometry, if you can emulate fractal patterns on an antenna and get the best of both worlds from a frequency coverage perspective, the little elements give you pretty good functionality at very high frequencies. And because there's so many zigzags and movements, moving and changing, the actual total length of the antenna is quite long. So you can get a fairly wide range, just like the log periodic antenna, you can get a fairly wide range of operation out of them. And Vivaldi antennas become quite popular recently. I've got an example of one here if anyone wants to have a look at one later. And once again, it's based on the slot antenna that we looked at before, but because the pieces of metal curve out, that slot changes width, and since it's a slot that actually radiates, you're covering from that wavelength down to less than a Mach head. So it's probably about a gigahertz to 8 gigahertz antenna. It has directional gain, polarization, and you can actually stack them. You can make them into other patterns. You can do lots of things with them. They're really cool. And something I've always been interested in is covert antennas, like how to have an antenna that no one knows is there. Not forgetting the safety pin. I'm into safety pins and paper clips. That's why I reckon this one's one of my favourite antennas. This is the paper clip Ossipol stick Yagi. You don't have to spend a lot of money making antennas. Take away from what I've just briefly talked about today is like how to get the best results out of your SDR antenna. Choose one that suits your needs. Do you want an omnidirectional antenna? Do you want something that's pointing just point to point, one place? Think about your polarization. Mount your antenna as high up as you can and as clear of any other obstacles as you can. Once again, think about low loss coax. Spend as much money as you can afford on the coax that goes up to your antenna, especially if you've got it up high. It's got to go up a chimney and around the wall and into your office or wherever. If you're doing receive only and you're not transmitting, it's a lot easier to use a low noise amplifier, which you can power through the coaxial cable and have that mounted up on the masthead or at your antenna junction. Choose your physical location to avoid interference. And if there's someone over here who's transmitting, you want to have your antenna as far away from them as possible. And if you have got interference you can't avoid, look at using filters. I've got a number of filters that are useful just for normal everyday SDR use, even with little stick antenna. Ones that block out the FM band, for example. So there's some serious power at around 100 megahertz from them. The paging services, the POXAG pages at like 149 megahertz can obliterate the 2 meter band sometimes. And so notch filters, band pass filters, high pass filters, low pass filters, they all have their place in optimizing the signal that you get. And that's all I've got today. And thanks very much for your time. And happy to